5.5 Standard Enthalpies of Formation. As you see in this reaction, CO2 formed by reacting carbon and oxygen gas. So we will call this reaction formation of the CO2, just forming from a simple element. And the delta H formation of that is given to you at a standard temperature and pressure. So you need to be able to write down the equation of formation equation of any component is given to you. For example, C2H5OH, I know there is a C, means this the carbon you have H means hydrogen gas you have, and you have O means you have oxygen gas. So these are reacting, and it will give you that. Now you need to balance. So you have 2 carbon here, you put 2 here, you have 6 hydrogen here, you need to put 3 here. Oxygen, you have 1, you simply put 1 over 2, because 1 over 2 multiplied by 2 is 1. So balance this. Same things here for H2CO3, you have hydrogen, you have C, you have oxygen gas, then you need to balance it. You can practice this question number A, B, C, and D. This is the page 332. Now, using the standard formation, knowing that the hydrogen H2 gas going to the H2, right? Kind of there is nothing. If the H2 form just simply is from H2. That's why the enthalpy formation of the pure elements are 0. So it stands for of the Fe, oxygen, Br2 are all zeros. So here, the standard enthalpy of formation of elements already in its standard state is 0. Just make sure. For example, for graphite, of course, it's going to be diamond. So you have enthalpy of the formation, but it's not going to be the same thing, right? It will be 2 different things. That's why. So here we have CaO plus H2O is CaOH. You want to find the enthalpy of that. So what we do? We can write the enthalpy formation of each component here. For example, for CaO is consist of Ca and oxygen O2. So you just write it down. The enthalpy formation, this number is given in appendix 6 at the end of the textbook. You can find it out. Enthalpy formation is given, it's negative 634.9 kilojoule per mole. We do it for H2O. So in the liquid form, it's coming from H2 and O2. And make sure you balance it as well. CaOH2, so you just write it down, the formation equation for the CaOH2, and the delta you can get it from the back of the textbook. Now you use the Hess's law. It's going to be your target reaction, and this is going to be the steps. For this one, CaO should be in the right side, the left side. That's why you multiply by -1. The coefficient is 1 here is 1. You just multiply by -1. For the second one, again, H2O should be in your left side, so you multiply by -1. The coefficient is 1 here and 1, so it's good. And for the last one, it is CaOH2 is in the right place. It's in the left here, in the right here, and here is in the right. The coefficient is 1 here, 1 here, so you don't need to change, or simply multiply by 1. Make sure when you do the change, you have to change your enthalpy here as well. Then you add them up. And see the addition is like that. Looking at that, it's like the delta H formation of the product is minus the enthalpy formation of reactant. See, minus delta H2 and minus delta H1. So generally, if you don't want to go through this long steps, you can say that delta H of a reaction, enthalpy change of a reaction, is the enthalpy change formation of the product minus enthalpy change of the reaction. Make sure you multiply by n, because this enthalpy changes is molar enthalpy changes. So if you have two more, you have to really multiply by the coefficient in the reaction. You have, for example, here it is 1, the coefficient is 1 and 1. So for this one, we say enthalpy formation of COH2, okay, minus enthalpy formation of CaO minus enthalpy formation of H2O. And then we have that. At the end of the textbook, you just make sure you have the right sign. Most of them is negative. And the delta H will be negative 65.4. So here is another one. So you want to find the enthalpy change of that. So from the back of the textbook, you get the enthalpy change of each of these components. So I know the delta enthalpy of the product minus the reactant products, H2O. H2O, the formation of that is negative 393.5. I think it's for CO2. Yes, this is for CO2. And since the coefficient is 1, so you just simply multiply by 1. Here, the enthalpy formation of H2O is negative 285.8. You have to multiply it by 2 because here the coefficient here is 2, minus the enthalpy formation of CH4 is negative 74.4. You multiply by 1 because the coefficient here is 1. And enthalpy formation of the O2 is pure element, so enthalpy formation of that is 0. 2 multiplied by 0 would be 0. You do that, that would be the enthalpy formation of this reaction. Since it's that molar enthalpy of the methane, so here the coefficient is 1. That's why you just divide this one by 1 to get the molar enthalpy. Molar enthalpy is the enthalpy for 1 mole. Here is another one. We do the same thing there. Here the delta, the H is changes, the enthalpy changes given to you. And what is the standard enthalpy formation of the benzene? You want to find the formation of C6H6. That's why this is your unknown. So again, product minus the reactant, as you see. And this one is kind of your unknown. The enthalpy changes is given to you. You just need to rearrange for delta H of the benzene. And you can get the answer. So you can do question number 2, 3, 4, and 5 for this page. This is page 335. So multi-step energy calculation using the standard enthalpies of formation. Before we know that the delta H is equal to the energy released into the system. And that the enthalpy change is equal to N multiplied by molar enthalpy. So when octane burns in an automobile engine, heat is released in the air and to metal in the car engine, but a significant portion is absorbed by liquid in the cooling system. An aqueous solution of ethylene glycol, it will be there, right? What mass of octane is completely burned cause the heating of 20 kilograms of aqueous ethylene glycol? Automobile coolant from 10 to 70. The specific heat capacity of the aqueous ethyl glycol is given C. So whether is produced as the gas after all heat fall into the concrete. So we need to write down the burning of octane, CHH18. This is the reaction. You need to balance it. And from the delta H formation at the back of the book, you can so that to get the enthalpy of this reaction, product minus the reactant, we do it, and this is the delta H of that reaction. Also, you know that this delta H is produced is equal to the heat produced by system. From the previous step, as you see, this is the molar enthalpy, right? This is the heat produced by 1 mole. So delta H is N molar enthalpy is equal to Q that is absorbed by the liquid. We arrange it for N, so the delta H goes into the denominator. Mass is given to you, but here, because the C is in gram, you have to convert this gram into kilogram. And then here the delta T is 70 minus negative 10, so initial final temperature minus the initial, you get 80 is given, and you just do it divided by the delta H that you got it from the previous step. That would be the N, the number of the mole of the octane is burning. Now we want to find the mass of that, so you know the mass is the mole multiplied by the molar mass, so we have that. Yep, that would be the final answer. Here is another example that you use multi-step to solve this problem. So one way to heat water in a home cottage is to burn propane. If 3 grams of the propane burns, a temperature change will be observed if all of the heat from the combustion transferred into 4 kilograms of water. So we just need to write the combustion of propane. So you need to know that is burning, it's produced CO2 and H2, you balance it. Use the delta H formation from the back of the textbook to calculate the delta H of the reaction. The amount of the propane is given, mass of the water is given, the specific scale as the water. The heat absorbed by water is equal to the heat produced by this reaction. See, delta H is equal to Q of water. Delta H of the reaction is N multiplied delta H enthalpy, and Q of the water is MC delta T. So we're looking for the change in temperature. So we arrange for the temperature. Here is M of the water, make sure. And the N, instead of the N, we can put M divided by molar mass. Make sure this is for propane. Just put T here. This is molar mass of the propane. And here you put mass of the propane divided by molar mass. Here's mass of water divided by the specific heat capacity of water. Do this calculation and the temperature change will be 9.6 degrees Celsius. To check your understanding, you can do question number 7, 8, 9, and 10.